Alrighty, so we're just going to pick up where we left off. We briefly talked about mutually exclusive events. So basically, if two sets contain common elements, it means they are not mutually exclusive. So, for example, if we're going to look at the set of integers between 1 and 5, inclusive, okay? If we talk about odd numbers, and can someone tell me another set of numbers that will have, well, it's got to have some overlap. Prime numbers. Okay, so odd and prime. Okay, if we look at odd and prime, we're looking at 1 is odd, 2 is prime, 3 is odd and prime, 4 is neither, and 5. Okay, so we've got some overlap because 3 and 5 are both prime numbers. Okay, so these events would not be considered mutually exclusive. Okay, whereas if we don't contain any common elements, then we're looking at mutually exclusive events, or they can be complementary or disjoint. I wouldn't be too fussed about the terminology there. Let's know what mutually exclusive and non-mutually exclusive numbers are. So an example would be odd and even. We happy with that? There's no overlap. The odd numbers are 1, 3, and 5. The even numbers are 2 and 4. So between the two sets of numbers, there's no overlap. Okay, that's called mutually exclusive events. Question?
Is 0 odd or even?
I don't think it's considered either. Okay, so here we go. We've got two sets of numbers, x and y. Okay, and we've got our new notation again, which is pretty much the only thing that's new in this topic, honestly. What does that one mean? Okay, so it's the union, okay, and it means or. Okay, so it has to fit one or the other or both. Okay, whereas the other one is called the intersection, and that one is the and. So it must fit both criteria for and. Okay, one little word makes a very big difference in probability. Okay, alrighty. So let's have a look at the union of x and y. Yeah, it's all the numbers. But only counted once, right? If we wrote 1, 2, 3, 4, 5, and then 2, 4, 6, we would have double counted 2 and 4. Remember how we talked about that formula, like P of A plus B of B, and then minus the intersection, because you've double counted when there's double. I don't normally think about it like that, to be honest, anyway. Just use a bit of logic. Okay, what's the intersection?
2 and 4.
Just 2 and 4. So we're just looking at the common elements, okay? Which numbers are in both sets? Okay, so have a go at that for B. Okay, so you're doing cut I and I for B. abbreviate, but just watch out. You know, if you write BL and there's black and there's blue, you've got to do a bit more than that to distinguish. Okay. So are we happy with the union? Okay. That or is usually a larger set or a large set, and then the intersection is just the overlap. My intersections are a little bit. There we go. All right. Anyone want to do this one? Is it just yellow and green that's common? Okay, great. So it's just what's the overlap? Yeah. Neither of these are mutually exclusive events because you've got overlap for both. Yeah. Alrighty. Have a look at the next one. Remember we looked at the Venn diagrams on Tuesday. Okay, so you're looking at rolling a die. So all possible results, you know, you're looking at this. Like you need to make a Venn diagram that's got A, B, and C there. Okay, so A is the even result. So you might want to start by drawing A. Okay. B is the odd result. How will B be attached to A?
Mutually exclusive.
They're separate. Okay, there's no overlap. These are mutually exclusive events. Okay. And C is the numbers less than 4. So how does C fit in then?
It can be in the middle.
Okay, it has to overlap for both. Are we happy with that?
Yes.
Okay. No. C would be
No, I done that.
the whole, all outcomes are the square. Okay, don't be too worried about your Venn diagram looking very pretty. Look at mine and then feel better about yours. Okay, so
What do you mean?
we've got A is the even result, so we're looking at 2, 4, and 6, but what's the problem with what I've done?
You didn't think of the ones to go between.
Okay,
C
which
and A.
what needs to go there, Dylan? Okay, what about 4?
Less than 4.
Okay, so watch out for that. Less than 4 does not include 4. Okay, that's not inclusive. Then we've got our odd numbers. We've got 1, 3, 5.
1,
But
3 go
again, yeah, bench.
1, 3 go between the C and B.
Okay, 1 and 3 are the intersection of B and C. Okay, and then we've got results less than 4. So what goes in here now? Yeah, nothing. So we've covered all of them, haven't we? And then what goes outside the circles?
Nothing.
Nothing, because we've covered. So if there was anything that hadn't been covered, that would go outside. Okay? It's often a rectangle. Alrighty, so now we've got our Venn diagram. It's kind of an interesting looking one. And we want the union of A and C. So what's that going to be? Sorry, Jamila? Yeah, it's all of A and C. Okay, so anything contained in either of those two circles, which is what numbers?
Everything but 5.
Everything except 5. You know, don't be stressed about the set notation. This is how we write numbers in a set. It's really no big deal. I would at least use square brackets if you were going to do it rather than parentheses. Okay. The union of C and B.
Everything but 4 and 6.
Okay, is everything in B and in C. So 1, 2, 3, 5. What's the union of A, B, and C?
Everything.
Everything. So when would you have a situation where everything wasn't included if we were looking at this? Where would that number be? Joel?
The outside of it.
Yeah, so if we had a number here, like if we looked at, I don't know, 7, okay, and that was here, then that would not be included. So this is the whole set of numbers. Okay, and then the intersection of A and B is...
How do you write that?
myself to remember how you write an empty set. I'm going to Google it. We won't need to write it like that. It's outside our course, but I think that there's some notation I am vaguely remembering from sets at uni. Oh no, so you do just kind of write it like that. For empty set. But you can just write here, like, no solutions or something like that will be fine as well. Okay? Which two sets are mutually exclusive? A and B. Okay, there's no overlap, which is why the intersection is empty. Yeah? Alrighty. So, I hope that you've well and truly started on those. We already wrote that down. Can you write it in again? Okay. So, a set of favorable outcomes is called an event. Let's think about rolling a die. Okay, so die is singular, dice is plural. It doesn't really matter that much, I suppose. People say dice all the time. For one. So what's an event? I'm rolling a die. Can someone tell me an event? Sorry?
Rolling a 4.
Okay, roll a 4. That is an event. 1 in 6 chance of rolling a 4 on a normal die. Ben, should you have a different one?
Even.
Okay. Roll an even number. Okay, hashtag means number. And what's another one? Okay, a multiple of 3s. These are all events. Okay? So, when we talk about activities that produce these events, we'd often refer to an experiment or a trial. Okay, so you might see after 50 trials, which is like 50 rolls of the die, okay? And all possible outcomes are our elements of the sample space. Remember sample space? Okay, you've seen that probably every year of your schooling. It's a very simple ability that we do. Okay, so if two things can't happen at the same time, that's our mutually exclusive, right? Because there's no overlap. There's no intersection, there's no and. Okay, another word for them is disjoint events. Okay, so let's go back to our rolling a die. What's an example of, sorry, that's an E, of mutually exclusive events?
Rolling even.
Okay, so roll odd or even. So these are your two events, rolling an odd, rolling an even, they're mutually exclusive. Another type, Bench?
Rolling a 4 and not rolling a 4.
Sure. Roll a 4 or not a 4. Okay, so your complementary events are going to be mutually exclusive. Yeah? Okay, so these events are also complementary, right? And if the events are mutually exclusive, then we can say, for example, the probability of rolling an odd or an even is probability of odd plus the probability of even. We're happy with that? Whereas when they're not mutually exclusive events, if you just add the probabilities together, you've kind of double counted some things in both sets, and you'd have to take that away, which we wrote down last time. Honestly, like, this is not how I think of it. Like, I just think of it logically rather than as a formula. So don't let this be something that makes you stumble in this topic. I don't think it's worth being stressed over. Okay, so can you have a go at this question? And you can look at the next one as well. Boys. someone help me out here? Probability that it will be a diamond or the king of clubs, Bench?
So it'd be 1 out of 52 to be the king of clubs, and then 1 out of 13 to be a diamond. So that was 13 out of 52.
Yeah, or 1 out of 4, either one. So Ben said 1 out of 52 for the king of clubs, 13 out of 52 for your diamonds. I mean, like, are we all happy that we would normally not even write this step and we just go straight to 14 out of 52 because it's somewhat logical? This is what I mean about not getting bogged down in the formulas, right? Well, maybe I shouldn't inverted commas the formulas on video. So that simplifies 7 over 26, is that right? Okay, so if we have a look at the next one, can you have a go at that as well?
Now a word from us.
Okay, so you're looking at cards from 1 to 15. If we look at it being a multiple of 2 or 3, can you see how this question is different? Because we've got some overlap. Okay, for more complicated situations, like it can be helpful to think of it as the subtracting, to be honest. Okay, so anyone want to help me out here? What was your thinking?
How many factors could be used to get 3 or 2?
Yeah.
So that'd be 3 different options? I get confused.
No, I think you got quite a few more than that.
10 out of 15.
How'd you get 10, Sam?
I just wrote out, just went to the numbers 1 to 15, and then wrote down numbers that you can multiply by 2 or 3.
Okay, so you kind of went through logically from 1 to 15 and you were like, 2's a multiple of 2, 3, 4, okay, and...
I miscounted.
Yeah? So we add them all up. We get 1, 2, 3, 4, 5, 6, 7, 8, 9, oh wait, and I missed 15, 10 like Sam said, so 10 out of 15, okay? Now, let's think about this, because if we were looking at the numbers from 1 to 100, right, we don't really want to write them out like this, do we? So this is where our kind of formula can help us. So we can think of it like the multiples of 2, okay, so if I would just take it back down to 14, so there are going to be 7 multiples of 2, yeah? So we got 7 out of 15, and then the multiples of 3, so 15 divided by 3 is 5, okay? So it would be 5 multiples of 3, and then I kind of go, okay, what are the ones that I've double counted? That's the idea of that formula, Joel.
Yeah, that'll be
like having to go, okay, 3, okay, there's 6.
I think, yeah, I know what you mean. I know what you mean, but I think it's probably still quicker than writing the list out. Yeah, I think so. But you're right, it's not the quickest either, okay? So then you've got numbers that are multiples of 2 and 3, so you've got 6 and you've got 12, yeah? So you're basically going through what are the multiples of 6 there, which you can kind of divide. So I'd take 15 back to 12, like the nearest multiple of 6 below, and then divide it, and you've got 2. So you can use it, and it would still be quicker. Oops, sorry, and that should be a subtraction, right? That's what we double counted, because we counted it in both sets, and so we get 10 out of 15, which is 2/3. But Sam did that with his list. Okay, we're stopping. Alrighties, now we're looking here for a multiple of 2 and a multiple of 3, which is the same as saying it's a multiple of what? Yeah, so if it's a multiple of 2 and 3, it will be a multiple of 6, okay, which might be an easier way to think of it for this kind of problem, to be honest, okay? Oh, that's okay. That is what I wrote. So we've got 6 and 12. Are we happy with that? Can I get some nods or shakes here? Okay. Alrighty. So this question here, I find the first one's quite odd, but just this is how you'll see some in your textbook, so it's just helpful to know what they're looking for. I think the question will be clearer. They're just trying to ask you, what does this mean? Okay? So from a standard pack of cards, one card's drawn at random. B is the event drawing a black card. D is the event drawing the queen of diamonds. Q is the event drawing a queen. So this is just asking, what does this mean? Can anyone remember what that means with the bar over the top, Amy? Okay, so it means not B, which means not black, which means red. Does that make sense? Okay, so really this is exactly the same as saying we're looking at the red cards. Yeah? But we're not asked for a probability here. That's why I was saying it's a bit of an odd question. It just wants you to interpret what it means. So this one here is very similar. It's not Q, which means it's not a queen. I mean, I'd probably still think of it as not a queen, okay? But it means it could be ace to 10 or king or jack, yeah? But we'll just leave it like that as not a queen. Okay, next one. Here we're asked to find the probability of B occurring, okay? This is really easy, right? What's the probability of picking a black card?
1 of
26 out of 52, or it's just a half, right? What's the probability that it's not black?
26.
A half also. Okay?
Isn't that the exact
Simple,
same thing?
simple.
What was the point of D?
Well, it's a different event.
But like,
D is the
there's
event
no
of drawing
questions.
a queen of diamonds.
No, sorry, D as
In the question.
D is the event of
Oh, I don't know. Oh, yeah, because we're doing more.
Oh.
Oh, we did.
Oh, we are. Okay.
Is the question the exact same?
Okay? Yeah, so it's the same information. Okay? Dan, that's extremely unhelpful, and I don't appreciate it. Alright, so next one, we're getting a bit trickier now, okay? So what is the probability of it being black or a queen? I'll let you go ahead and answer this slide, okay? Do have a go. Even if you're not quite sure, have a go, okay? And then you can just change it if you've made a mistake when we go over it. This 29 out of 52 is simple as it goes.
Wait, a diamond's black? Or
It was.
No, diamonds are red. So diamonds and hearts are red, and clubs and spades are black. Okay. Oh yeah, sorry, because it's black cards.
Bingo.
Is it 7 out of 13? Does it simplify
Oh,
too?
yes.
Okay, so I would just think of it as there are 26 black cards, okay? There are 4 queens, but you've already counted 2 of them. So I'm kind of doing the subtraction in my head, I suppose. So I'm just adding the 2 red queens there. Job. Okay, next one. Black or the queen of diamonds. So you've got 26. The queen of diamonds isn't included in that, right? Does that simplify 27 out of 52? No?
Not black.
D is
If you've got a question, ask, yes? What's the probability that the card will be black and a queen?
1 out of 26.
Okay, so there are 2 black queens in the deck, right? So we're looking at 2 out of 52. Next one. Not black or the queen of diamonds. So just remember, not black in cards means red. Okay, so sometimes when it's written as a not, it can be helpful to think of what does that mean it is. Okay, but not always. It depends on the situation. Bench?
1 over 52 because there's only one card, which is diamonds, queen.
But it's
This is an or question. Okay, so it fits either category. So if it was and, there would only be 1. But we're looking at how many?
1 over 2.
Yeah, so we want all the red cards and the queen of diamonds. That's already been counted, right? So when we count the red cards, the queen of diamonds has already been sorted out.
Successive.
Okay, now you may or may not have known that Josh loves to dress up.
Oh, he does, doesn't he?
In his dress-up wardrobe, Josh has 4 shirts and 3 pairs of shorts and 2 pairs of shoes. Who can tell me how many dress-up combinations he can wear?
Oh,
Don't call it out. Who knows how to do this? There must be more than one person that knows this trick.
Just multiply the
Okay, how do you work out how many different dress-ups Josh has? Rachel?
Don't you just multiply them all?
You know you do. So you do what?
4 times 3 times 2.
That's it. It's super easy, right? So it's going to be 24 different combos of Josh looking fabulous.
Right on.
That might not work.
So basically, when we look at successive outcomes, okay, so this is one thing after another, or even if we talk about it at the same time, we treat it the same as one thing after another, but we use this multiplication principle, which is super handy, okay? So it means that you've got 3 decisions to make, okay? So Josh has to choose a shirt, he has to choose some shorts, and he has to choose some shoes. Oh, that wasn't. Oh man, okay. And so how many choices does he have at each stage when we multiply them together? Now, if you did this, you could write a list and kind of like work that out that it's 24. We're not going to do that because we have seen this before, okay? But super handy. All right, now this one's from the question. No, it's not meant to be Joel. This is Jolie. The textbook chose that name.
Joel says.
At a school sport day, Jolie runs 100 meters, 200 meters, and the 400 meter races. Each outcome, we're looking at it as he either wins or loses. So we're keeping it fairly simple. It's a bit of a negative way to look at a running race, isn't it? Can we make it he wins or he...
Yes, participation awards.
Okay, so how many possible teams, just waiting, I'm waiting. How many possible outcomes are there for the 3 races? Okay, so what we have to see here is we've got 3 successive events that occur, right? So that means I would use underlines, okay? So like it's often called the box method. Boxes are longer to draw. So I usually do underlines, and then you need to fill each of those spaces with a number, okay? So the first race, the 100 meter race, he can either win or lose. So there are 2 options here. In the second race, he can either win or lose, and the third race, win or lose, right? Does that make sense? So it's really what we just talked about. There are 8 possibilities. Okay, so what's the probability of him winning no races? 100%. It's not you, Joel. It's Jolie, all right? Bench?
Would be half times half times half, so 1/8.
Okay, Bench says it's a half times half times half. What do we think?
How many people in his race?
There's 6.
How many people are in his race? And let's not go being like Jonathan and George, right? If you have 8 people in your race, You do not have a 1 in 8 chance of winning. You don't. Like, that is a terrible way to think. If you are running against someone who's way better than you, they're going to beat you, okay? Unless they fall over.
Rangers gets like 5.
You don't know. Now, so, just look, you will find often in these questions, come on, I know it's my fault. Often in these questions, you will see a lot of like horse races tend to come up, and they'll make this really very silly disclaimer where they say each horse has an equal chance of winning, which is just totally untrue. But they make it so it's a single situation, right? We don't have that information here. I wouldn't expect that you're going to be tricked by something like this, okay? But remember just that we were talking about skill matters, okay? So those were not equally likely outcomes, our winning and losing. Okay, let's look at a more simple situation. A coin is tossed twice. Sorry, I'm just waiting for the people who are talking over me. Okay, a coin is tossed twice. We're going to draw a tree diagram. Hopefully you're familiar with these. Like I said, there is nothing other than the union and intersection notation that you haven't seen before in this topic. Okay? So, a tree diagram starts at a point. Okay? It starts at a point. And then you have the first event is your first set of branches, and then the second event is your second set of branches. So, our first event is the first coin, right? Now, when you toss a coin, how many options do you have?
2.
Yes, who's the punk that says 3? You don't have 3. You show me when it lands on the side, okay?
Well, actually, 50
I ask you and I'm like, I know every time someone thinks they're hilarious.